What I was just talking about is what the operating system can do. For example, like MAD-wise, I can tell the OS when you plan to read specific pages. For instance, with mlock, I can tell the operating system not to swap memory to the hard disk. This includes using AppSync to tell the operating system to sync the hard data of memory to the hard disk. In reality, this is similar to some operations in databases. It's a kind of mmap that can do to some extent replace or have similar functionality. However, it doesn't have a better optimized way from the core perspective. This includes optimization for specific pages, buffers, queries, and other related optimizations. So we hope to put these operations on the database and let the DBMS be better at it. For example, OS is good at correctly ordering these pages or flashing 30 pages to the hard disk. OS can do some specialized prefetching and replacement strategies in this buffer area. For example, what everyone calls LRU, least recently used related strategies, are very good at what they do. However, databases are actually better at it. They are better at things like flushing 30 pages to the hard disk in the correct order or doing some specialized prefetching. Their buffer replacement strategies, like the one mentioned for LRU, are very good at what they do. When it comes to file storage, at the most basic level, databases actually store data as files. In this sense, operating systems are like databases. They don't need to understand what these files are for, whether they store configurations, metadata, indexes, table structures, or anything else. Only the database management system knows. For example, some databases might use a multi-file hierarchical structure. Like large commercial databases such as Oracle DB or DB2, others might use a single file structure, which is simpler and used by smaller databases. However, the operating system doesn't know the meaning of these files because they are encoded in a specific way by the database. So in terms of database management, the operating system is not our friend. Only the DBMS knows, as the files are encoded in a specific way for a database to understand. This is a database storage manager, a component responsible for managing the database data files. It represents files as a collection of pages and tracks which data is read or written to these pages, as well as how much free space is available in them. Its main purpose is to improve the locality of pages in terms of space and time. It also tracks the configuration of written data and available space. In essence, it's a central, pivotal component of a database. We can also see that a page is actually a fixed-size data block in the configuration. The database organizes data into one or more files, which are stored in pages. These pages consist of fixed-size blocks, and a configuration can include different types of data, such as tuples and indexes. However, most commercial database systems do not mix these data types within a single page or configuration. Generally, indexes are stored separately from tuples. For example, indexes and tuples are not usually stored together in a complete collection, including raw data, metadata, logs, records, and so on. Each configuration has a unique identifier, and the DBMS uses an intermediate layer for scheduling, which can map the configuration ID to the actual physical location on the disk. If the data is in a single file, the page ID can be represented simply by the offset. However, most database systems have an intermediate layer, such as hashing indices or B-trees, to map the ID to the file's offset path in a specific relationship. So the storage manager we discussed earlier performs a related conversion, converting these page IDs to file paths and offset, and then mapping them to the actual physical addresses on the disk. Alright, let's talk about database pages. Most databases use fixed length pages instead of variable length pages. Why? It's mainly to avoid the engineering overhead required to support variable length pages. When a page's length is variable, the system needs to support varying lengths, which can be complex and costly in terms of storage management. For example, if a page is variable in length, the system must track and support different lengths, such as 4 KB, 8 KB, or 32 KB, which adds to the engineering overhead. This information, including the actual length of each page, would need to be stored, which increases complexity and management efforts. Using variable length pages can also lead to fragmentation issues. For instance, when a variable length page is deleted, it can leave behind fragments of different sizes, 4 KB, 8 KB, 16 KB, making it challenging for the database to efficiently fill these fragments. This process would require additional overhead for addressing and flushing the pages to the disk. In contrast, using fixed-length pages avoids this complexity and ensures that each page is a consistent size, making it easier to manage and reducing the likelihood of fragmentation. In most databases, page sizes typically range from 1 KB to 16 KB, with 4 KB being a common and practical choice. Let's also discuss the fault-tolerant write levels, which refers to ensuring data consistency in the event of failure during write operations. When we talk about fault-tolerant write, we are referring to the autonomy of writing operations to storage devices, such as hard drives. For example, if the hard drive's page size is 4 KB, the operating system will attempt to write 4 KB to the hard disk. If this 4 KB write operation is not entirely successful, perhaps due to power failure or other fault, the operation will either completely fail or succeed. There's no partial success in writing. Now, when designing a system, this has implications if the database page size is larger than hardware's page size, such as an 8 KB database page and 4 KB hardware page. Additional operations are needed to ensure the safety of writing data. In this scenario, there is a risk of partial writes. For example, if 4 KB is successfully written, but the remaining 4 KB is not, the system could end up with partially written data, which can lead to data inconsistency. To address this, additional mechanisms for fault-tolerant writes are required. This is why fault-tolerant write levels are defined in databases to handle situations where database page sizes exceed those of the hard drive and operating system. When designing a database, it's crucial to consider these factors. Once we surpass these limitations, we need additional safeguards to ensure the data safety, atomicity, and consistency. Well, this concludes our section for our database system nodes sections. Welcome to our CnosDB community. Our CnosDB Cloud is alive now. You can join our CnosDB Discord in our channel. We will see you next time. Bye bye.